So before you start Lab 5, what you should do is to download both the MATLAB binary file as well as the three functions listed in steps 1 and 2 of the lab itself. So I will start here by loading up the MATLAB binary file, and this data, this MATLAB binary file contains a number of variables that are associated with the 5 stations across the Columbia Basin and into the Palouse. And see the variables listed here. We have elevation, latitude, longitude, the name of the station, climatological monthly precipitation, climatological monthly downward shortwave radiation, monthly high temperature, monthly low temperature, and wind speed. And all of the data are in units that are it's all in metric units. So there's no data conversion um, needed here in terms of unit conversion. So the first thing that we can do is to calculate potential evapotranspiration, and this is done using the function monthly PET underscore PM. Okay, so this is going to run the monthly Penman-Monteith equation on the climatological data that you send in, and the format that you send it in is listed here. You have to send it in that format directly, otherwise you're going to get garbage out, garbage in, garbage out. Okay, so we can run that forward and we'll get some values for PET. You might want to look at those values just to see if they look reasonable. It's always good whenever doing any sort of data analysis to check your data along the way to be sure that you are getting results that look generally what you would expect them to be. So this is monthly accumulated potential evapotranspiration. So column 1 here is January. Column 7 is going to be July. So we see these pretty high numbers in July, potentially evapotranspiration of somewhere between 170 and 185 millimeters per month, whereas in January it's 6 to 8 or so. So that, it looks, at least at first glance, that looks reasonable. So that's good. And the next step here is to run a loop over your data. So we're going to run a loop over the 5 stations, and what we're going to be doing here is we're going to be calculating the simple hydrologic model, where we send in precipitation and potentially evapotranspiration. The hydrologic model gets run, and it gives us in return the monthly evapotranspiration, the climatic water deficit, as well as runoff. So we'll run that forward through time. And what I might mention here as well is that you can actually send in the default here is that the hydrologic model assumes you have a water holding capacity of your soil of 150 millimeters. That can be changed if you wanted to change it. So if I wanted to change it, I would just put in some value here. So if I had particularly deep soils, I could put in 250 and I get some slightly different answer that comes out of it. Okay. So after doing that, what we can do next is we can look at some of the values. Again, it's a good idea. Let's look at actual evapotranspiration. And what we see here is we again see these values that look like between 6 and 8 for January, and then in July what we see are again values that are much higher, although you notice here at this site number 5, the values are quite a bit lower, and that's actually one of the warmer sites. And I should mention that the variable name will actually tell you the order of the stations. So here the order is listed from the easternmost station, or Elk River, to the westernmost station, or Connell, Washington. So Connell, Washington is it's a more arid environment, and hence we see in July that the actual evapotranspiration is quite nominal. Hence the deficit is going to be quite high. Okay. The last thing that we can do is actually plot this up for a given station. So let's clear our figure and let's type water balance, and this particular function Water balance graph 2, it requires you send in precipitation, actual ET, climatic water deficit, and potential evapotranspiration. So let's actually look at the water balance for Connell, Washington, since we were just talking about it here. So we'll change this to number 5 since it corresponds to the 5th station. Okay, and then let's take a look at that particular station here. Okay, and while we're at it, let's make one other figure so we'll compare. So figure, so this will open up a new figure, and we'll run the water balance graph for Elk River, which is located much further east, receives much more in terms of precipitation, and has less potential evapotranspiration. Okay, so here are the two stations. It's probably a good idea here to put a title on the graph. So that second plot I'll title as Elk River. The first figure I will title as Connell, Washington. Okay, and then we can take a look at those two figures side by side. Okay, let's make it a bit bigger. There we go. So in this function, what's nice is that you're actually plotting 4 different values. They all have units of millimeters. And the nice thing, again, with thinking about the water balance is that we end up combining measurements of energy, which is potential evapotranspiration, with units of moisture, like precipitation. So we can look at these graphs, and there's 4 data points per month. The blue line here shows us our monthly climatological precipitation. Okay, so again, far more precipitation in Elk River than in Connell. The green line is showing us the dashed black line is showing us our potential evapotranspiration. You can see that it peaks right around in July is the most the month of the year we have not necessarily the highest solar radiation, although actually we do have a little bit higher solar radiation in July than June because cloud cover tends to be a bit higher in June than in July. We also have warmer temperatures, so that those two factors, along with things like wind and dew point temperature, help to emphasize the peak here in July in terms of potential evapotranspiration. The actual evapotranspiration is the green line. It's always less than or equal to the potential. And in places like Connell, it's actually far less than the potential. In fact, you start running into deficits, basically where your potential is greater than your actual evapotranspiration in April. And so the red bars here are showing us the climatic water deficit, or basically the difference between the potential and actual evapotranspiration. One way to think about it is that if you wanted to maintain a crop, a reference crop, in this case it's grass, if you wanted to maintain a grass surface that was water unlimited, in other words, its constraints on growth were not water, you would need to irrigate basically this much that's shown in red here per month. So you'd have to irrigate on the order of 175 millimeters per month in July. You can contrast that with Elk River, where we see only 3 months of the year where we actually have a deficit in the climatic water, and it's particularly acute in August and a little bit in September. And then, of course, the rainy season picks up, and you can see in October there's actually more precipitation than there is potential evapotranspiration. So a good contrast here between an arid environment and a more mesic environment, much wetter.